We can separate mixtures by physical means. And one example, it's not in your book, but I feel like it's necessary, is distillation. And that separates a mixture of substances based on differences in boiling points. Now this right here is a distillation of water. Water is, like if you get it out of your tap, is going to be water, H2O, maybe some table salt, there's going to be some magnesium, calcium, fluorine atoms in there, and so on and so forth. And if you heat it up with a Bunsen burner, the water inside there is going to eventually boil. And we know it boils at 100 degrees Celsius. Once it starts boiling, it will rise up through this tube, hitting the thermometer, which will read 100 degrees Celsius. It's stoppered off up here, so it will travel down through here as a gas. But surrounding that tube is an outer tube right here that has very cold water running through it. So that will recondense the vaporous water into the liquid state in here. And you'll get that. What would be left over is pure water on the right in that Erlenmeyer flask, and you would have the salts left over in here. The reason that works is because salts have a very, very, very high melting point and a very, very high boiling point. Water doesn't, so they're easily separated by distillation. Most distillations are usually two liquids. For example, moonshiners distill alcohol. They're removing the ethanol from the water. When you make alcohol, there's always going to be a lot of water there. Like beer is only, let's say, 5% alcohol. But if you want to get the strongest liquor you can, like moonshine, you can distill it. So the boiling point of ethanol is around 76 degrees Celsius, and the boiling point of water is 100 degrees Celsius. So as you heat it up, the solution of those two, the ethanol with a lower boiling point is going to get into the vapor phase before water does. So if you're heating it up and it's at 78 degrees Celsius, that's not enough energy to boil or vaporize water. So inside the flask, it's going to continue to be a liquid, the water part. And the ethanol will boil and evaporate, and it will go up through the tube as well, and down into here, and then over there you'd have pure ethanol, and over here on the left in your original flask you'd have water. Filtration can also be used to separate substances, and it does it based on differences in size. And so there's a picture here of a mixture, and the man or woman is pouring it through a filter paper, and you can see, maybe you can't really see, let's see if I can zoom in. Yeah, the liquid, the filtrate in there is clear, whereas initially it was yellow. So the yellow stuff would remain behind in the filter up here. An at-home example of filtration would be using a colander to filter out spaghetti and water. The spaghetti is too big to go through the holes of your colander. Water is small enough to pass through, so you've filtered something. All right, another method that's mentioned in your book is chromatography, and chromatography separates mixtures of components based upon differences in polarity. Now, on the PowerPoint that I've posted on Blackboard, there is a video demonstrating the use of TLC, or thin layer chromatography, and you can watch it being done I'm not going to put it in this here because it's honestly kind of an annoying song to listen to, so you might want to mute it if you do watch it. But what it does is, you can see here, is it separates things. So the person might, in this case, has A, B, C, and D, different types of mixtures that they've spotted on that start line, and it's probably an ink. And they take this piece of paper with the spots on there and they put it into a flask, like over here, with a solvent, as like that stuff right there. And the solvent will run up the paper through capillary action. When it interacts with the, in this case, ink, it will dissolve some of the ink in it, and solubility depends upon polarities of things. Like oil doesn't dissolve in water because it's nonpolar, and water is polar. So the paper has a certain level of polarity, the solvent has a certain level of polarity, and so does the compounds that you've spotted onto the paper. The interplay between all three of those polarities determines how fast the spots run up the paper with the solvent. So as you can see here, this spot ran up, and as the solvent went up, it separated into what looks like 3 different colors: red, blue, and yellow. The yellow and blue are still intermixed here, giving you the green, but if it was allowed to run longer, they would separate completely. And so that is probably black. It's probably a black spot put there initially. The second spot with B is just yellow. You can see there's no other color in there. So that was probably a yellow spot. The third one has, if you look very closely, there's yellow right there. And there's blue up at the top with green in the middle. You can see the yellow is smearing all the way up here. It's probably doing it there as well. Notice they go the same length. The blue is smearing a little bit, but where the blue exists along with the yellow, you get this green portion right in the center here. Eventually, if this was allowed to run even higher up, it would separate completely. But that would, since it's blue and yellow, would give you a green spot ultimately down there. And then on the far right, in the fourth one, there's only a red dye, so that spot was probably red. But this ultimately is how we can separate compounds if filtration and distillation don't work. Every compound has their own special level of polarities, so we can separate them that way.